8.7, ladies and gentlemen, the exceptions to the octet. So in this section, you're going to find out some depressing news when NAS doesn't work, okay? So the octet rule is so simple and useful at introducing basic concepts that lead us to help how atoms bond with other atoms when they obey the rules. However, there are some exceptions, and it just makes me sad that my law will just still be a theory. So I'm going to show you helpful hints when you know not to even try NAS, and what it's I like to call, you got to go old school with the dots, okay? So 3 main exceptions. Over the years, I have seen tricks to help myself know when NAS won't work or when NAS will work. So number 1, if molecules or polyatomics have an odd number of electrons. So you know, like when you do like NAS, and the need will always be an even number. But if that available is an odd, when you subtract those, you're going to get an odd number. Divide by 2 is still an odd number. You're going to get like a something 0.5. Well, ladies and gentlemen, you can't have half of a bond. You either have the bond or you don't. But the NAS can work, and I'll show you. Actually, it's the first thing I'm going to show you. Number 2. Molecules are polyatomics in which the atom has fewer than octet. So like boron is a key one to this. Metals will never have the octet. Hydrogen will never have the octet. Okay, so there's 3 main exceptions. Molecules are ions that actually have more than 8, and it can exist. And what happens is the ones that usually do this actually have valence electrons more than 4. So I'm talking about valence electrons between 5 and 8. They actually can have what's called expanded octet. So you will see this topic, okay? So definitely the NAS won't work for these expanded octets. So let's go number 1. What happens if you get an odd number, okay? So I even gave you some examples of ones that actually have odd numbers. So the vast majority of molecules are polyatomic ions. The total number of valence electrons are usually even. So it makes the NAS work very nicely. However, I know that nasty word, however, in a few molecules in polyatomics, such as these ones right here, you actually get valence electrons. You actually get an odd set, okay? Complete pairing of these electrons are impossible, so an octet around each atom cannot be achieved. So for example, let me show you this one. The NAS will work, but who's the one that gets the odd electron? So let's say it's nitrogen monoxide, NO. Okay, no, I'm not trying to tell you no, that's nitrogen monoxide. So right here they need 8 plus 8. 16, but available, what happens is it's nitrogen that's going to kind of screw this up. He's an odd valence electron because oxygen's even, and you're going to get 11 and subtract and divide, and you get 2.5 bonds. Well, I just said you can't have half of a bond. So if you notice the structure, there are 2 possible structures, which means it has resonance structure, okay? So right here, you would put the odd kind of dot right here, this lonely 1 dot, you would actually put it on that nitrogen. But you could also put it on the oxygen. So in one case, this one does have 8 valence around it, but this one only has 7. But in this case, nitrogen has 8, and this one has a 7. So remember in 8.6, it's a blend of the 2 structures. So either structure is possible. But ladies and gentlemen, if you get an odd number of something 0.5 for the bonds when you do NAS, then obviously one of the atoms will not have the octet. And it's just like lonely electron just sitting there by itself. Okay? So draw some possible ones. So let's see when this works. So nitrogen dioxide. And unfortunately, you won't know if it works until you actually try the NAS. Okay? There will be times where I tell you don't even try NAS. It's not even worth it. But in this case, we can still try it. Nitrogen dioxide, I need 8 and then 8 times 2. So 16 plus the 8 is 24. And then nitrogen has 5. See, nitrogen's going to kind of screw it up for us. And then O has 6 times 2. So 12 plus 7 is 17. And then you subtract and then divide. And I'm going to get 3.5 bonds, which means somebody's going to have a lone electron. Well, nitrogen has to be in the middle, oxygens on both sides, and you got to have at least 3 bonds. Got to have at least 3. So it looks like we're going to have a double and a single. Okay. The oxygens, they'll have their octet. But usually the one that had the valence number that's odd, you would usually see that one lonely electron at the very top. And that's okay. It happens. Okay. I can do resonance structure. And basically, I'm just going to move a double bond to the other side. So a single and a double in lone pairs. And only 2 lone pairs here, but that nitrogen is still going to have that lonely electron. Okay? So those could be 2 possible structures. Could I make one of the oxygens have that single electron, but maybe make nitrogen the octet? You could. I don't draw it because these are the 2 structures that are mostly possible, but it could have another one where one of these oxygens would actually have 7 and the other one has 8 and then nitrogen has 8. Okay? If you do the formal charge, you would notice that these 2 are the actual preferred structure. So this is, NOS still works. However, if you see that odd, then usually this odd one, that 0.5, usually goes for the atom that had the odd valence electron. Okay? And just so you know also, if we would have drawn NO2 -1, that's why we usually see this polyatomic NO2 compared to this gas NO2. Because by gaining 1, we'll help fix that odd problem. So just giving you a little side note there. So this one right here versus this, you won't have an odd electron when it gained that electron. Okay? What happens if you actually have less than the octet? Okay, and I gave you some examples. So what happens is with less than the octet, boron, aluminum, and you're noticing I'm talking about group 3A here. Okay, it's because they only have 3 valence electrons. So what's the most they can do? They can only do 6. I mean, that's the most. So you will never, ever, ever see lone pairs because they can't get to 8. It's not even possible. So you kind of almost have to think old school with the dots. So a second type of exception occurs when you have fewer than 8 valence electrons for any atom, molecule, or polyatomic. So this situation is very rare, very, very rare. With the exception of hydrogen and helium, we already know hydrogen and helium will never get past that 2. Never, ever, ever. Actually, I'm going to put that in highlight because I want to make sure we remember that. So most often, it's boron, aluminum, beryllium. But the cool thing is, NOS still works. So we're still seeing happiness. NOS will still work for us. But we have to remember when we do the need, boron only has 3 valence electrons. So he can only get up to 6 electrons surrounding him. Same thing with aluminum. Or if I was going to do gallium, anybody in group 3A, anybody in group 3A, they all do this, okay? Metals do this also, okay? And I know Juan, you asked me about this one before, beryllium. AP loves to throw beryllium in this topic because beryllium sometimes does share those electrons. Sorry about that. Does share those electrons with nonmetals more. Okay, they sometimes call it, they have properties of nonmetals a little bit with beryllium. So I don't like how they put him in this category because he's a metal. He shouldn't even be talked about right now. But anybody in group 2, they technically could do this. But you got to remember group 2 is a metal. And because group 2 are metals, they're going to do ionic. which is called give and take. So we aren't talking about metals right now. However, beryllium is group 2, has 2 valence electrons. He technically could do 2 bonds, which means 4 electrons around it. So you're going to see beryllium pop up again in chapter 9, when chapter 9 is all about nonmetals, but he will pop up again. Okay? So in this, I want you to focus on these 2 elements. Okay? Even though aluminum's metal, I get you. I get you. I just want you to know, anybody in group 3A, they will never, ever, ever get to 8 because they only have 3 valence electrons. Okay? So group 3A, only 3 valence electrons. So same thing with gallium. Only's got 3, indium, thallium, all the same, okay? So we have to remember the math for boron. When you do the NAS, we already know hydrogen needs 2, but times 3 because there's 3 of them. But when you do boron, you got to remember it's 6, not 8, okay? And that's why students are like, you know what, Rodriguez? I'm better with the dots because that way I won't forget boron doesn't need 8. And that's okay. You want to go old school with the dots? Boron 3 valence, hydrogen coming in 3 times? Pretty simple, okay? You don't have to do the NAS. I'm just showing you that the math does work, okay? So with hydrogen coming in, they're going to create a bond. Going to create a bond. Create a bond. Easy peasy. Please do not do this connect the dots stuff as your final answer. Make a more cleaned up version of this because AP hates when they see connect the dots. Okay, so that's what boron trihydride would look like. Let me show you the math real quick. That way you can see it. Boron needs 6, but he has 3 valence. And hydrogen has 1 times 3. So when you go 6 times, or 6 plus that 6 is 12, and then 3 plus that 3, and you still get, the math still works, 3 bonds, okay? Same thing if I did it for aluminum. Aluminum has 3 valence electrons. I got 3 fluorines coming in, not rocket science. But you got to remember, fluorine has 7 valence electrons, so you're going to automatically form that bond between each one. The math will work, ladies and gentlemen. If you don't want to do it, that's totally fine with me as long as the picture looks correct. So your cleaned up version, and you could have put that fluorine on the bottom. Either one is fine. But the point is, notice that central atom for each picture for boron and aluminum that I drew. Each one only has 6. Only has 6. And that's okay because they'll never get to 8. So you have to remember these exceptions to the rules. So group 3A, definitely exceptions to the rule. Just like beryllium group 2, he will only get up to 2 bonds, 4 electrons. Okay? So far, not too bad. NAS still works. But now the topic that just kills me, what's called expanded octet. They actually can get more than 8. That's why it's called expanded. And you'll see this name somewhere pop up in the notes in just a second. So unfortunately, NAS won't work. I'm going to tell you, don't even waste your time. But you have to be able to recognize when this happens. That's the hard part. Once you recognize that it happens, the drawing's easy. But when does it actually happen? So like I said, I like to call it old school with the dots. Like we just did up here. Draw the dots, connect to see who's going to bond with who. So there is a trick, okay, that Fairbraw has come up with, and I'm not going to take credit for it because I didn't come up with it. He noticed a trend that usually beyond right here, period 3, so this shaded region right here in yellow, atoms that are beyond this 3, they usually can do more than the octet. Okay, so you're talking about right here, you're talking about 5 valence electrons, 6, 7, and 8. It's these ones right here. They can do expanded octet. Now, nitrogen, oxygen, fluorine, they can also. So I'm going to put right here, can also, but it's usually the shaded yellow region that does it the most. And it's because of this thing about the d orbitals. So elements from period 3 and beyond usually have unfilled d orbitals that can then accommodate additional electrons. So elements in periods 3, 4, and 5 can be a central atom that is hypervalent. And hypervalent means that it can accommodate more than 8. More than 8 surrounding hypervalent, sorry, it's been a day today, hypervalent, I know I'm going to keep saying that. It can surround more than 8 on that central atom. So because the central atom has a large size, very key, it can accommodate extra electrons around it. You don't always see nitrogen, oxygen, and fluorine do this because they're smaller, but it can happen, just not as much. So because the central atom, for anybody in here in this yellow region, because their central atom is so big, they can actually accommodate more. So I'm going to show you a couple tricks that I've seen over the years to help you with this. So size plays a role in it. The larger the central atom, the larger the number of the atoms of electrons that can surround it. The size of the surrounding atoms are also important. So expanded octets occur often when the atoms bonded to the central atom are smaller and most electronegative. That's very key that you understand what they're trying to say there. Okay? So what they're saying is whoever this central atom is, expanded octet occurs when the atoms bonded to the central atom are smaller. So these guys sitting out here, and notice I'm going to say expanded. Notice right here, now I have 10 surrounding it. Whoever these are smaller than the central atom. And that's when you usually see these guys. Fluorine, nitrogen, oxygen, hydrogen. Okay, even going to throw hydrogen in there too. Actually, well, I don't want to throw him in there because he's saying right here more electronegative. But you will see hydrogen usually surround some of the stuff. So the central atom is bigger in radius, and usually the surrounding atoms are smaller. Now this is AP talking to you. If you can draw a Lewis structure in which each atom obeys the octet, do it. If you can obey the octet, do it, do it, do it. AP exam will never ask students to decide on their own. So when drawing a Lewis structure, whether they should obey the octet or expanded, in order to get a formal charge, they want them to be as close to 0 as possible. Okay? This is so important, this tip right here, because AP has never came out and said this until this summer. They've always said that students have to figure out when expanded octet happens or not. They're telling you literally from this summer, when the craziness happened with AP, you won't be asked to decide on your own. They will tell you when it happens, okay? And when drawing the structure, they want you to obey the octet as much as possible or expand the octet to get a better formal charge, okay? So all the ones I'm going to show you right now are all expanded octet, okay? And I will now follow AP's rules, and I will also tell you when it happens. So I'm going to give you some tricks. So number 1, don't do NAS. It ain't going to work, okay? I don't know why, but it always comes out like 3 bonds, but when you do old school, you actually see 5 or 6 bonds. Number 2, you will always recognize this when a subscript is 5 or more. So notice some of these subscripts are 5, 6, okay? They will always be expanded octet. So always expanded octet. Always, always. Just over the 20-something years I've been studying chemistry, I see trends and I remember it to teach students. Just unfortunately, I'd rather have my NAS work though, but I just can't get it to always behave. Number 3, I've seen this happen also with expanded. When halogens bond with other halogens. I don't know why, but you're going to get expanded octet. Okay, and the only thing I could think of is because they have 7 valence electrons. Now you're also going to see some noble gases in here. You're going to see some xenon. You're going to see some krypton. Don't freak out. We know that they bond with fluorine. Okay, so here we go. We're going to go old school with the dots. Okay, so phosphorus, 5 valence electrons. Fluorines have 7. Okay, I'm just writing that down. Phosphorus is my central atom. And I'm going to draw it over here because we're going to do a cleaned up version also. So here comes my phosphorus. And he's got 5 valence electrons. So I'm going to put 2 on top. And I don't want you to think I'm trying to do like some star pattern. I'll put my lone pairs on top, 1 on each side, and then 1 on the bottom. Now, you have 5 fluorines coming in. You automatically have to put a fluorine with his 7 valence electrons around these 3 empty spots where they have these lone pair, this base, I don't want to call it lone pair, this unpaired electron. So you're automatically, there's your bond, there's your bond, there's your bond. But where are the other 2 going to go? So this is what happens with the lone pairs on central atom. You can split them just like that, at an angle. So if you look at it, it's like almost 90-degree angle. And you get fluorine, and it bonded with that phosphorus. And you get this fluorine that bonded with that phosphorus. Notice the phosphorus. How many does he have surrounding it? Well, let's do a cleaned up version. And I do not need to see how you did it. I just need the cleaned up version. So this is what it'll look like. So now the question is, how many electrons are surrounding that phosphorus? Phosphorus doesn't have lone pairs no more. Those lone pairs split to bond with fluorine. And right here I have 2, 4, 6, 8, 10. So I have 10 electrons on the central atom. But no matter what, every surrounding has to always meet the octet. So no matter what, with expanded octet, only the central atom is the expanded octet. Your surrounding atoms always have to be the octet rule, always. Unless it's hydrogen, then he will not have lone pairs, he will only have that 2. Okay, so this is why I say go old school with the dots. Okay, but please, please, I don't want to see connect the dots. Let's do sulfur. Sulfur has 6 valence electrons. And I got 6 fluorines coming in. Okay, so with my 6 fluorine, we already know that each one of these is going to take a spot with fluorine. These 2 are going to get 1 on the sides. But then these lone pairs on the top and bottom, they're going to split just like that. And now sulfur doesn't have lone pairs anymore. And that's totally fine. So right here, oops, sorry, I was drawing dots again. So I'm going to get fluorine with my lone pair, and this fluorine, and then these 2 are going to split. Like I said, it almost looks like 90-degree angles. No matter what though, every fluorine will still meet the octet because they're surrounding atoms. So right here on the sulfur, if you count it up, Oops, let me do it in a different color. The sulfur has how many surrounding it? So 2, 4, 6, 8, 10, 12. 12 electrons surrounding it. But all of the fluorines still meet the octet. So remember, ladies and gentlemen, what they mentioned above here. You still have fluorine, small atom, surrounding one of these bigger central atoms. And notice we just used phosphorus and sulfur in that group 3. So they will always be the central atom. Let's do a couple more. What if I do the same thing with sulfur, but then only put two less fluorines? So we only put 4 fluorines on it. So remember, sulfur has 6 valence electrons. So automatically, I have to put 2 of my fluorines on those empty unpaired electrons. But then where do I put the other 2? Now, very key here. You can split lone pairs, but you can't split one pair and then another pair. So I have an option down here. I can split, or I could take these lone pairs and I can split to put the other 2 fluorines. But my point is, ladies and gentlemen, you can't do something like this up here and up here. Because now you have these 2 lonely electrons not even paired to anything. So you can't do that. So pick one of them and split it. So I like to usually leave lone pairs at the top. You can leave the lone pairs at the bottom. Okay, and then that's what it would look like. So you'd have your sulfur, fluorine, still has its octet. But now down here, we split those lone pairs. So it looks like sulfur has its octet. But remember, there's still 2 lone pairs on that sulfur. So how many electrons are surrounding that sulfur? And there's only 10 electrons surrounding it. So each bond has 2, so 4 times 2, and then the 2 lone pairs that they're at the top. Let's do another one. So same thing, sulfur has 6, and I have 2, only 2 fluorines. Well, that's good because I got those 2 spots right there. So right here, fluorine, and right there, fluorine. And that's okay. Sorry, my phone is going crazy right now. So when I draw this, I'm going to put a fluorine on each side. And the fluorine will still have its octet. And that fluorine will still have the octet. And now the question is, how many does sulfur have surrounding it? And he actually now has 8 also. So 2 bonds plus the 2 lone pairs. And that right there is okay. So I wanted to show you 3 different ways how just taking a couple fluorines off could give you expanded octet, but in this case you actually have your 3 atoms with its octet still being met. Let's do a couple others. Like I told you, anytime you see halogens bonded to halogens, and it doesn't matter how many halogens they have, it's still like, don't do the NAS. NAS, don't even waste your time. It ain't gonna work. Go old school with the dots. So every halogen always has 7 valence electrons. This guy has 7 valence electrons. So bromine is a bigger atom, so he's going to be in the center. We already know fluorines are smaller. So when I put my dots, 7 valence electrons, and I got 5 fluorines coming in, I automatically have to put one of them right here. Okay, and there comes fluorine with his valence electron. But where am I going to put the other 4? I have all this possibility. Okay, well, I can put 2 of them over here, but they're going to have to split. So you're going to get this fluorine up here and that fluorine up there. But where do I put my other 2? I can put them on top, I can put them on the bottom. But the point is, you can't just put one on top and one on bottom. You got to split lone pairs. So I'm going to split these bottom ones. And like I said, when you split them, make them look like they're 90 degrees. And then I put my fluorines surrounding it, just like that. So my cleaned up version, like this. One going across, because I didn't split this one. But then down here, I did split those. So while I'm drawing my dots, how many electrons are surrounding that bromine? Well, I got 4 bonds, but I also have a set of lone pairs. So 2, 4, 6, 8, 10, there's 12. 12 electrons surrounding it. I think the most I've ever seen is 14 surrounding it, but I don't know if there's an actual 60 one out there, but you could see 14, a lot of 12s, a couple 10s, but it does happen. Here's another one, chlorine, and no, that's not carbon, iodine, fluorine, that's chlorine. And you already know chlorine is a bigger atom than fluorine, so he's definitely in the middle. Central atom, he's got 7. Okay, he's got his 7 valence electrons, and then fluorine, automatically, I got to put one of the fluorines right here, because I got that empty, lonely electron right there, that unpaired electron. So there comes one fluorine. Now where do I put the other 2? When you have options, go to the other side first. So I'm going to split this side. Could I have done the bottom? Yes. Could I have done the top? Yes. But like I said, when you have options, ladies and gentlemen, you want to see them away from each other. Okay? And it would have that structure. It is not wrong to choose the top or the bottom. It is definitely not wrong. So I'm going to draw my cleaned up version. And before you ask, when we practice in class, do you have to show like 2 different drawings? No, just give me one. But please, ladies and gentlemen, you show connect the dots. And if you have no clue what I'm talking about, it's like when students do this, and they draw the line, I can literally still see the electrons. And you literally just drew a line between the 2 electrons. No, AP gives no points for that, because you are literally just connecting 2 electrons and creating a bond. The electrons turn into a bond. They didn't connect a bond. They created the bond. So no connect the dots. Okay, so give me a cleaned up version. So now if you count this one up, chlorine has 2, 4, 6 electrons and bonds, and then these 2 lone pairs. So he has 10 surrounding electrons. I wanted to show you a noble gas one too. So right here we have xenon. So putting some notes here, noble gas. And then I got a couple ions to show you also. So right here, xenon, noble gas has 8 valence electrons. And you know fluorines has 7. So automatically with xenon, and I wish I had the research to actually read how they were able to get fluorine to bond with that xenon. But I've never been able to see that type of research. I don't even know how stable or unstable it is. I've heard it's unstable, but it was successful in bonding. So with the fluorines, you literally just pick any of these lone pairs and then just split them. So maybe I pick this one on right here. Let's split it at a degree like that. So my cleaned up version, just got to have this. And every fluorine, oops, those dots look terrible. It's really hard drawing dots with the stylus because they want to kind of mush together. Just like that. Okay. So now with the xenon, you have 2 on top, 2 over here, 2 over here. That's 6, 7, 8, 9, 10. So xenon, I know it doesn't look like the central atom, but he is the central atom. Look at the atom, kind of if you rotate it about 90 degrees down, then you would see that he is still the central atom. So he has 10 surrounding electrons. What if you did it with an ion? So if you notice where arsenic is, arsenic has 5 valence electrons and every fluorine has 7. Here's what happens. Arsenic has 5 valence electrons. Now look at this, ladies and gentlemen. You got 6 fluorines coming in, but only 5 available spots. I mean, you're definitely going to have a fluorine there, fluorine there, fluorine there, and then these two are going to split. That's 5 fluorines. Where's the 6th one come in? And this is where this homie right there, -1, he helps out arsenic. You're going to actually gain an electron to help the central atom to make that 6 fluorine bond. And maybe just put it right here. And that's where it goes. So now your 6 fluorine can bond right there. So let's get a cleaned up version. So this one right here was fluorine. One down here. But then these lone pairs split at the top. And then this one lonely electron then gained an electron, and they also split, just like this. Molecules have shape, and you're going to learn those shapes when we get to the next chapter, chapter 9. Right now, we're just drawing it like it's two-dimensional, okay, just on paper. So now for arsenic, 6 bonds, no lone pairs, so it has 12 surrounding electrons. Okay, let's do these two. Iodine, here's another halogen with a halogen. Okay, so an H, halogen with a halogen. But this time it's going to gain an electron. Let's see if you can figure out what's going to happen. Okay, and I couldn't even see my subscript there. Hold on. Oops, there you go. So iodine, 7 valence electrons. Okay, and you got 4 chlorines coming in. Okay, so automatically I got to put 1 right here, but then another 2, I got to split a pair. So maybe I'm going to split these 2. Okay, well now that's 3 chlorines, but where's the 4th one got to go? Okay, so remember this guy? Remember that guy right there, -1? He can help out this spot right there. Okay, so there you go. He can help out iodine by putting another one there, because if I put my 4th one right here, ladies and gentlemen, if I put it right there, I got this lonely electron that was paired, and now he's unpaired. He ain't gonna like that. Remember, they want to be paired. Even if they're not bonding with anybody but themselves, they still want to be paired. You just made it unpaired. So we're not going to do that. So we're going to add this extra electron to the central atom, and now we can create our chlorine bond. So our cleaned up version looks like chlorine came here, chlorine's down here, but then iodine still has his 2 lone pairs. Oops, chlorine. I got so used to writing fluorines. It takes time, ladies and gentlemen, to see this, okay? I've been doing this so long, I could see it without NAS. Even creating NAS, I could see it without it. But you guys haven't had the chance to do this. So this is what happens. I totally forgot. With the gaining of the electrons, I do need to put this in brackets. Same thing with up here, because arsenic gained. You still got to put it in brackets. So even if it's expanded octet, still do it. So down here, how many surrounding electrons do I have? So 2, 4, 6, 8, 9, 10, 11, 12. Okay. SO4, -2. So what you're going to get is you're going to get sulfur, 6 valence electrons, and 4 oxygen. Automatically, I got to put 1 oxygen here and 1 oxygen right there. And then my other 2 oxygens, well, I can just split it up. Split these ones, or split the ones on top. But I have to split a pair, and then I fill it in. So you get this. All right, so we have our S and our 4 oxygens. But then I did a little pause there, ladies and gentlemen, because I completely forgot. We gained 2 electrons. Okay, so I completely totally didn't see that -2. So I'm going to clean this up. Okay, all right, so let's do our oxygen one more time. I'm sorry, do our sulfur. It's been a long day on a Friday afternoon doing videos for you. Okay, so give me a little chance there. All right, so I'm going to have my 4 oxygens come in, and definitely got to put 1 oxygen on both sides. Okay, and then I have to take 4 oxygens, but remember I have 2 extra electrons coming in. And it's a very special type of circumstance where you can actually have 2 different structures. One thing happens like this. If you go old school with the dots, 1 oxygen here, and I know you're like, wait a minute, Rodriguez, you said I can't just split and have this lonely electron. What happens is these 2 extra electrons, one of the oxygens, they're kind of missing when you go old school with the dots, and you can create something like this. Oops. All right, apologies. Sorry, my phone keeps blowing up with messages. All right, so right here, it's a special circumstance where you can actually create 2 double bonds that looks like this. Definitely expanded octet. So when you look at this sulfur, if you count it up, you have 6 bonds surrounding it, so you have 12 electrons. I have also seen, and AP would have to tell you this, okay, apologies, ladies and gentlemen. Sorry, my son is out playing and my phone is blowing up with messages. Okay, all right, back to this. There is another way you can draw this with single bonds. Something like this instead. We're now gaining the 2 electrons. The gaining of the 2 electrons would then be with the oxygen instead of the sulfur gaining the electrons. This is a very complex structure. AP would have to give you some assistance with this, and usually what they do is draw the structure and they give you questions about it. So I have seen it both ways, and if you Google it, Google the sulfate ion Lewis dot structure, and I guarantee you're going to see both of them. And you're going to see other versions too. So it could be this version with the oxygens on both sides. Now these oxygens with the double bond would only have 2 sets of lone pairs. The oxygens on the side, they would only have 3 lone pairs because they're single bonds. Regardless, you would still have to put it in brackets to show that it gained 2 electrons. And same thing right here. Sorry, I'm just like out of room. Gain 2. Gentlemen, but I promise we will go into more detail with this in class because I want to actually show you how the dots come about. Either structure would be acceptable on the AP test. So either the sulfur can gain the electrons, or the oxygens on the outside would actually be deficient in the electrons. So the sulfur gets the extra 2, or one of the oxygens gets the extra 2. Okay? So that is how to draw expanded octet. Okay? Definitely, this one right here is a very complex one. But remember what AP said right up here. You are never asked to decide on your own. They would have to give you some assistance. And that's good, because I will tell you that assistance